Working. Hello. Okay, I think that's working. If that, can you hold this one? If there's anyone asking a question, putting it back, make sure the question is recorded.
This mic on? How do I turn off?
It's always on.
Maybe
Uh,
like
No, you can let it on. It runs for like 10 hours, so don't worry about the batteries. Sure.
just keep it here. That's
Oh, sure, you can keep it here. Okay. I have some professional setups. like I'm a just like I'm a YouTuber. No idea. Hey, that's
How do you share both at the same time?
I guess I just quit and like do it this way.
Yeah.
That's the best way I can think
Yeah.
about.
Yeah. No, that's good. That's fine.
Okay. I okay. Can you open up the Zoom and check if everything works fine from your screen? Yeah, Teams. Because if I log in with my same account, it shows something doesn't looks right. Test 1, 2, 3. All right, attention everybody. We are going to get started. So for the first 30 minutes, actually first 10 minutes, we're going to have some quick lectures on what we're going to do. I'm going to give a quick lecture on the FPGAs, and then I'll go through the logistics. For those who haven't collect your FPGAs, don't worry about it. I'm not going to straight into the project right now. Starting to feel thirsty.
Yeah.
In the beginning. Okay. Right. Good to hear that. All right, so this is our lab 1. Get started with Vivado and BASYS3. I know you already went through Vivado and BASYS3 in the last semester, maybe LOD, but this time I give you a fresh start. I assume you have no idea about it. I'll give you a fresh start from scratch. So table of contents, that's the contents for today. Part 1, that's going to be the introduction to FPGA and hardware design procedure. This is from my industry experience, so you'd better just take it. Part 2, the lab task, using Vivado and build a 4-bit full adder. Usually the full adder is gonna be a whole semester coursework, but I'm not going to do that for this semester. Part 3, coursework introduction and task 1 assignment. So for task 1, for each task, I assume you finish in a week, but you haven't finished in a week, I won't blame you, but you are going to examine everything in the end of the lab, okay? So the learning outcomes of HAD is about how to make trade-offs between performance and area complexity in your hardware implementation. You will get hands-on experience on hardware procedure and FPGAs, debugging your hardware implementation, learn about hardware description language, which is system Verilog in this session. And you are going to learn about hardware design flow and using CAD tools, which is Vivado. Part 1. Introduction to FPGA. So what is FPGA? Starting from the very early days, we don't have many fancy stuffs. You only have individual transistors like the one shown on the top right. But as the technology goes beyond, we are having more and more transistors integrated together. But the problem is it's getting harder to design because you have to manufacture them to test if there's a bug in your design. So in 1980s, genius in Xilinx, actually he founded Xilinx. They invented the first FPGA, which is programmable logic. And starting from then, we are having more and more transistors. And today we are having 100 more billion transistors on one single chip, like NVIDIA 5090 or Apple M3 Ultra. So what's next? Where's FPGA stands in the whole IC area? Like on the top left, we have CPUs. That means they are the mostly flexible in software. You can program whatever program you want, but they are not as fast as you think. And on the bottom right, we have the ASICs. The ASICs means application-specific integrated circuits. They can do one tiny task very, very fast. like crypto mining, things like that, but they can do nothing else. So FPGA is something in between. It's in between CPU and ASICs. So it gives you the flexibility to design your own IC, while it gives you the flexibility to program your own IC. So if you look inside what's inside the FPGAs, we will find three important blocks. One is reconfigurable functions. Those are the logic blocks. And we have reconfigurable interconnections. These interconnections are basically networks connecting different logic blocks. And finally, we have the reconfigurable input-output. These are going to be the physical I/Os on your FPGA board, like the push buttons or the switches. And in this session, we're going to use the switches and displays. Okay? But different vendors have different kinds of FPGAs. For example, Xilinx and Altera, they have different designs in the basic blocks. But you don't have to worry about what's going inside the blocks, because the EDA will hand out all the programming part. So in a typical FPGA, like the one in our hand, the BASYS3, it's got around 33 kilo logic blocks. Some other typical chips has around 10K to 100K logic cells. But the state of the art is the AMD Versal VP1902 FPGA. It has 18.5 million logic cells. So you want to do some CPU design work, like the real CPU design work, this is the FPGA you are considering to buy. All right. So from this lecture, you will learn about the FPGA design procedure. On the diagram shown on the right, this is basically the it's not just an FPGA design procedure. If you want to get into a company like AMD or Intel, this is something you have to remember. This is going to be the IC design procedure. So step one, you have to design the architecture, like what we are learning in the lectures. Basically, you draw your block diagrams and cook your circuit specifications. In the next part, you are going to write your own RTL or HDL code. Basically, you are going to use Verilog or VHDL to describe your circuits. Then you are going to do some simulations. When you are trying to do simulations, you have to make your own test bench. The test bench has two parts. One is input, which is the stimuli, drive your circuits. And the other part is the tester. It reads the output from your design under test and check in whether it fits the ideal function as you are trying to design. By the way, if you have any questions regarding to the process, you can always stop me. So step 4 is synthesis and DFT. This part is going to synthesize your code into a gate netlist. And sometimes it will add the debug cells if it's needed. So the netlist is the file that actually describes the gates and the interconnections. And you are going to build some constraints. The constraint has two parts. One is the I/O bonds, which is the connection between your code and the FPGA board physical layout. And the other part is constrain the timing requirements. Since our design is pretty much simple, we don't have to worry too much about timing requirements. The next part is implementation. As I just showed you before, the logic cells are not the gates as you are trying to design. Instead, they are the LUT cells designed by the FPGA vendors. So the implementation part is usually provided by the FPGA vendors to compile your netlist into the physical layout on your FPGAs. And finally, you have some timing area analysis to make sure all your design requirement is met. Finally, you are going to generate your bitstream. So this bitstream is the thing that downloads to your FPGA and make it run. We're going to go through the whole all the steps in this session. All right. So part 2 is lab 1, which is implementing a 4-bit full adder on BASYS3. For those you have a Windows laptop with Vivado installed, please open your Vivado. Okay. We're going to start a program from scratch. I'll pause here for a while. If you have any questions, you can always raise up your hand and pause me here. Yes? Sorry, what? If you haven't installed yet, I suggest you download the web installer. Okay. I have already uploaded the Vivado installation guide online on Keys. You can check them later if you haven't have Vivado installed yet. Because Vivado installation process takes about 30 minutes to 1 hour. If you're worried about missing this part, don't worry. Everything is recorded, including the sound or everything is shown on the TV. Everything is recorded. If you have trouble with running Vivado right now, you can always check the labs later on Keys or YouTube.
Part 1, right? Next time we will start the coursework.
This time we will start the coursework. I put the coursework introduction in part 3.
Yeah. Oh, so we're gonna do all of it.
Yeah. So basically, I will show you some techniques about working with FPGAs, and then I will give you the instruction to the part 1 coursework, and we're going to take them as a take-home work. Okay, cool.
But
Yes.
no
I'll
problem.
okay. I'll jump into the logistics. Since I'm having some questions regarding to Mac users, I'll jump into logistics first. So for students who have a Windows or Linux laptops or desktops, you just need to install Vivado, straight easy. For students who don't have a Windows or Linux laptop, you can use the Cloud VM, but it's not ready yet. But you can also use the NMES Student Lab at King's Building. It's KIN 425. We have set up every workstation with a Vivado installation on the lab on the workstation in the lab. So in the lab, they will have 40 workstations for you to use, and the lab is open 24 hours. You can always go to the lab and play with Vivado. So basically, this is the Cloud VM. Cloud VM is a remote Windows workshop. You have the link to the Cloud VM. And for all users, you will connect, have a virtual Windows online. But unfortunately, we don't have Vivado installed right now. I'm still pushing the IT system to make sure it's installed. So I skip this part. But the basic idea is you can have a Windows access on the browser. Okay. It's not connected. Okay, now it's connected. Also for the Mac users, you can download the Windows app. And log in with your K account, and you will see this Cloud VM. But still, however, we don't have Vivado installed right now. So my suggestion is go to the student compute lab. We have around 40 workstations, each with a Ubuntu system and Vivado 2025.2 installed. You can write code, run simulation program, debug on BASYS3 using these workstations. You are suggested to use GitHub to sync and manage your code because you don't have too much storage on these workstations. But also, files are synchronized across the workstations. Like if you save your code and project in one home folder in one workstation, it will synchronize to other workstations as well, as long as you log in the same account. So you don't have to worry about your data privacy. You as the account holder are the only one who can access the data. Only other people using the workstation cannot see your work. So the prerequisite, it's preferred you have a Mac with Intel CPU or PC with x86 CPU. If it's Mac with M series chip, no, it doesn't work. If it's PC with ARM chip, no, it doesn't work. All right, another pause session. If you can, you can pause me if you have any questions. Yep. Pay 425.
425. Okay.
All right, raise up your hand if you have a Vivado open. Okay. Okay, 1, 2, 3. We have only 3 with a Vivado. 4, 5, 6, 7. Okay, cool. 8. Basically, you can log in with your K account and you can use a Windows on in the browser. But I'm still pushing the IT department. They should have the Vivado installed, but they haven't did it yet.
By the end of the week.
Hard to say. You know, the logistics are. But we can always go to the student lab. It's opening 7/24 hours, like the physical lab.
Do you think it can be done before the coursework too? The cloud thing, can it be done before the first coursework too?
It's hard to. They didn't give me any guarantees.
And we aren't able to install it ourselves.
As no. But you can do simulation on Mac OS as well. I'll show up some tools later. Yeah, Vivado only works on Windows. But there are other tools other than Vivado. Yes, other than Vivado. So Vivado is not the only option, but you are going to struggle on Mac.
Even if we use like the cloud to help us figure out the other tools.
Yeah, it could help. It could help. But the problem is generating the bitstream. Like even you can use other tools and play with the design, you can't download them into your FPGA because you need Vivado to compile your code into the bitstream. You can ask some other, maybe go to the lab to help you to compile. On Mac, there's open source tool called Open FPGA Loader that can download the bitstream to the FPGA on Mac. But the problem is, yeah, that's how.
Will you send out an email to the IT team gets the cloud?
Yes, of course. I'm still pushing them. I'm not sure if they can do. They can finish it by this. I'm not sure you can even finish by the semester. They're running super slow, and I write my own script to help them install Vivado on the workstations.
Oh wow.
But I have no access to the cloud VM. It belongs to some other IT teams. So that means I have to elevate the problem to higher level.
You can't use emulators, right? Because those only work on Intel Macs.
The what emulator?
Paris crossover, like no.
Oh, actually, you can.
Even for an M1. Yeah.
Oh, actually, I'll show you. You can run Vivado on MX, but the problem is you can download the stream on the because they have problems with the driver, so that's a problem. But I guess you can open Vivado, compile it to bitstream, and then come back to macOS, use the Open FPGA Loader to try download it to the FPGA. But the problem is you are not going to debug with Vivado because there's a interact between Vivado and the board, so that's a problem. So I suggest go to the lab to do the homework. All right. I hope you have Vivado opening, and I'm going to show you how to start a project from scratch. And you don't have to worry about it. It's gonna be super simple. All right, I'll try to show my slides here. Maybe they can see it. All right. So this is lab 1, implementing a 4-bit full adder on BASYS3. I hope for the ones who have a Vivado, you'd better follow me step by step because all the following courseworks will be like based on this project. So make sure you even though you don't have a Vivado running right now, make sure you understand what I'm trying to do here. Okay. So in this lab, you design, simulate, synthesize, implement, and program a ripple carry 4-bit full adder on BASYS3 FPGA board using standard Vivado workflow. You write the RTO to the adder, verify it with a simple test bench, applying pin and timing constraints to map the inputs and outputs, which is the LEDs, and including carry out, generate the bitstream, and finally download it to the board to validate the correct operation on the onboard I/O. So that means in this semester, you are going to use the equipment on the FPGA boards, including the switch, the buttons, and the 7-segment display. So I'll show you a quick demo about what we're trying to do here. This is a quick video. So basically, this is a running FPGA board, and this is basically a 4-bit adder. On the right 4 switches are the data B, and the next actually data A, and the next 4 bits are data A, and we have one C-in input. So I expect you all play with your FPGA board and you do exactly what I'm doing here in this video. All right. So background about 4-bit full adder. This is the ripple carry 4-bit adder. Basically, you use 1-bit full adder to implement a 4-bit full adder. And this is our architecture design. In this design, we're going to put 1-bit full adder together and generate our 4-bit full adder. So this is the code I provided to you. You will have them on Kits. There will be an archive on Kits, and you can download all the codes. But the best way I suggest you to do is just copy the codes on the slides, okay? So now I have shown you the full adder.v. So this file explains the 1-bit full adder. And you can create one full adder.v file and put it in somewhere in your folder. You can post me if you have a question. Okay, since you all have the slides, I think the best way is I show you both slides and what I'm going to try to do here. So the first file will be the full adder.v. I suggest you have a folder called source, and you put the full adder.v here. So this is basically the full adder, the code. I'll zoom in so you can see it. So put all the codes in one file, okay? That's the full adder file. And on the top, I explain how the full adder works. All right, the next thing we're going to do is making a full adder 4-bit.v. So what I'm doing here is combining the full adder into one file that allows you to calculate a 4-bit digit. So this is going to be it. I just copy all the codes into the full adder 4-bit.v. Also, let me know if you understand the code or not. I can explain that to you. the keys. I have uploaded all
Did
the.
you upload them?
I think there's an archive
Oh, that's it.
has all the codes.
Downloaded this file. I'm trying to open it and wouldn't enter.
What? Wait, no way. I think it's I uploaded zip file.
Yeah, they unzipped it and then they tried to run it.
That's weird.
Yeah, like they tried to open source.
And
Like,
they don't see anything.
No, it's
And-
empty.
Okay, that's pretty weird. Let me try to. Yeah, I have all the file here. I basically upload this zip file.
Can you try open Vivado here?
Yes, of course.
See what's went wrong. To try open instead of create.
Oh, wait. Oh, there's no project file. It's just the source code. I'll show them how to start a project file from scratch.
So
If they open Vivado, they don't see anything.
so they just get the code.
They just get the code. Yes.
Okay.
They don't even need to copy and paste. In Vivado, I'll show them how to import the files.
Okay. Let me let's try another.
All right. By the way, actually, I'm just trying to show you all the codes here. So then you have a now you have a full adder 4-bit.v, and you are going to write the test bench. So here I try to implement a very simple test bench. The test bench, all the codes are actually uploaded to keys. But if you don't have it, you can always copy the codes from the slides. So this is a full adder 4-bit test bench. Now we're in the simulation part. And you are going to make a constraint file for IO mapping and the top file. And this top file is the interconnect between the 4-bit adder you made and the physical devices on the FPGA. If you have some questions regarding to it, I'll show you right now. But I have to give you the concepts before I go into the actual practice. You also need to know what is IO mapping and top file. The top file for this lab is shown here. It is basically the IOs interconnecting between the physical IOs and the circuit you design. And on the right, I show you some data sheet from BASYS3. So you see that all these devices shown here, they are connected to the specific kind of IO port in here. So this is going to be the data sheet you are going to read to make your constraint for IO. All right, let's not talk about the bullshit. Getting started with Vivado and creating a project from scratch, okay? Now open your Vivado. You should see nothing from your Vivado. This is how it is going to be like. Why is so large? Okay, it seems my Vivado is super zooming, but you can have a clear view on my Vivado as well. So the first step is create a project, okay? Now you have nothing, you just create the project. Shoot, what is going on?
Yeah, I was having the same issue. Like I can't open the file.
The files.
Yeah, like I can't open projects and select the files.
Oh, okay.
Can you like explain to them how I can't?
Sure. So sorry, what?
Like about it?
Yes. What do I say? I try to share it here. Okay.
Like they're trying to open project
Yeah.
and then selecting the file that they downloaded from you.
Oh,
No,
so
not
they don't see the files.
Yeah, like
They don't
try it.
see the source file.
Yeah, try it. So go on the bottom, click open.
Open project. No. They can't open because there is
Yeah.
no project.
Yeah, I think you should explain it to them because
Alright.
they're confused.
Okay. If you try to open project, it doesn't work because we don't have a project file right now. I'm going to teach you create your own project file, okay? So it's not like AOUD. You don't have a template right now. You are going to make your project start from scratch. So open your Vivado and click Open Project, okay? Is everybody following me? Make sure you just follow me and let me know if you have any questions. Now you just click Next and name your project. I just call it Lab 1 and put it somewhere. All right. And this is the next step. Let me know if you're struggling with Vivado. So this is pretty simple. You just get started. I just start from scratch, okay? Create project, next, and name your project. I'll just name it as Lab 1. I'll put it somewhere. I just put just on local disk D and create a subdirectory. And I'll say it's a RTL project. Then click next. Now this is where the part you have to add your own source files. For example, I have already shown you all the source code, including the all the source file for the full adder design. If you go to the keys and download the archive, you will see these 5 files. So now I'm going to add files. And open these 5 source files. Is everybody following me right now? If you have a problem with it, you can always stop me, okay? Right, okay, no problem. Next, make sure your target language is Verilog, not VHDL, because that's gonna cause some trouble. And don't select these two. You don't have to scan the RTO and you don't have to copy the source into the project. And then you click next. So the next step is adding constraints. At the moment, you don't have any constraint files, but you will create one later manually. I'll show you how to do it. And then select the default part. In the slides, I have shown you that the default part is called XC7A35 TCPG 236-1. This is a FPGA device used on your BASYS3. So I copy the device name here and try to search it. You will see the device here. If you don't see the device here, that only means one thing. You didn't install the package. You have to reinstall in Vivado and make sure all the 7 series package are installed. All right, click next. Now this is your project, your new project summary. And click finish. Now you have your project ready from scratch. While this project is scanning, Vivado is way smarter than any other EDAs. It will automatically find your top files and list the hierarchies. For example, if I go to the source, I open the top here, you will find all the files are listed in the exact way that we designed it. So you see the hierarchy here, and if you double click it, you will see the source code on the right, and you can always try to edit, okay? So this is the Vivado project panel. Now assume you have all the source code and you are trying to make your simulation. Go to simulation, run simulation. Don't click it right now. Make sure you right click it and go to simulation settings. In the simulation setting, you will find the simulation top module name is top. This is wrong because our simulation file is called 4adder 4-bit TB. The TB means the test bench here. You'll find it is not in the simulation folder. So you right-click your 4adder 4-bit TB and move to simulation sources. Anybody have problem with this step? Otherwise, I'm going to click it. Okay, now I just moved the test bench into simulation sources. So you go to the simulation sources and open scene, you will find two files here. One is top, one is 4adder 4-bit TB. Again, you go to run simulation setting, and you click the 3 dots. You can select the 4adder 4-bit TB as the simulation top module name. So this simulation top module name is different from the top file for the FPGA. The top file for the FPGA is the file connecting the FPGA I/O to the design. Well, this one is connecting your test bench to the device under the test. Now you click OK, and then you can left click run simulation and run behavior simulation. Right, after this simulation is run, you will see an arrow here. That means where the program is checking right now. Because I'm having a finish statement here. That means the simulation finish here. Then go to untitled one. You will see some fancy waveforms. So in this waveform, you are going to check whether your output or the waveform behavior fits the circuit that you design. For example, I have A and B and C in. Ideally, the sum should be A plus B plus C in. So let's check. In the simulation, in the first time step, I give 0, 0, and 0 for C in. So the output is 0. That is so much correct. And in the next session, in the next time step, I give 1 in A and B and 2 for B. And just as expected, the sum is 3, which is A plus B, okay? And for the next time step, I have A equals to 3, B equals to 5, and I have C in equals to 1. That means I have a carry in. So for this step, I'm actually calculating 3 plus 5 plus 1. And that gives me a 9. So this is how you simulate and test your own code and make sure it is designed in the way that you want. So I looked through all the waveforms, and I'm pretty sure that the sum, which is the output, is just as the sum of the input. I can zoom it, I can open it, I can do whatever I want with the waveforms as long as you can want to play with it. But make sure you just check the waveforms and make sure all the outputs are exactly the way that you want. So now I just checked my codes and I make sure everything is working. The simulation shows the code should be working, so I close it. I just close the simulation like this. All right, the next step is open elaborated design. In the elaborated design, Vivado will analyze your design and generate automatically a block diagram. So let's check how it goes. All right, my design is elaborated. As you can see, I have a 4adder 4-bit here. I have this 7-segment display module here. The 7-segment display module is on the top file. It will take the output from the 4-bit adder and it will display it on the actual 7-segment display, 7-segment display on the FPGA. If I click the add sign here, you will see how these 4 adders are connected to each other. And this gives you the 4adder 4-bit schematics. And again, if you want to look into the details inside the full adder, you can click again and you see all the gates in the circuits. So this is another way of making a verification to make sure Vivado gives you the circuit diagram that is exactly the same way you want, okay? So elaboration process helps you to debug your code and make sure the design circuit is exactly the way you want. Now I have already checked my code and I'm pretty sure they're connected in the way that I want. So I click run synthesis. And you see a design runs on the bottom where the synthesis is running. Again, you can always post me if you have any questions or you are struggling on Vivado. Wait. I want to make sure the question is recorded, so please talk to the mic.
So the step before this one, where you had a bunch of different blocks, what was that? Because I saw this one is the elaborated design, but what was the bit before this?
The step before this is run simulation. You mean how to get this block diagram?
But I saw that like on one simulation, you had 3 tabs at the top.
Yes.
One of them was like untitled one that had like
Yes.
the 013. We
Yes.
have 2 of them, but we don't have the other one.
Like,
We didn't see like an open new or anything
okay,
like
I'll check your.
that. Can you run simulation?
Check your simulator.
Can you go to the one simulation?
Oh yeah, no worry about this one. You don't have it wrong. Okay. Let me check your simulation setting. It's TV, right? And
You had 3
wrong.
tabs on your one, and we just had 2 of them. But maybe this time it will work.
the tab doesn't matter actually.
Oh, like, yeah, now that entitled 3, we didn't have that before.
Oh,
but
okay. Because every time you close your simulation, it saves a untitled waveform diagram, and if you close it and you reopen it, it will generate a new untitled waveform.
Okay.
So that's what's happening. And yeah, you have all the signals here, and that's all you need. If you click zoom in, you can see all the waves in here.
Okay, thank you.
Okay. If you want to open some more tabs, if you want to add more signals, you can just do it in this way, or like double click and make sure where it is. Like, because the reason I'm having more tabs because that might be I click some duty and I checked other codes. So you can always try to click it and play with it. You see all the tabs like going around. Okay. Let me know if you have more questions. All right, again, you can always post me if you have any question or you're stuck here, because the next step is going to be implementation. Oh yeah.
I added, so if I go to hierarchy,
Yes.
simulation sources contain the test bench.
Yes, that looks right. You run some. The process cannot guess another process. It means some other simulator is already using it. I don't know what's going on with
Is there a way to like terminate any other simulations that are going on, like a bit like how you control C?
Yes. So if you want to run simulation, make sure you close your simulation first.
Oh. Okay.
That's how it works. Okay, so now you close it. You have you are in
Yeah.
the project manager. Now you can run your simulation. That's the way. That's the way it is. So make sure you keep track on the window.
Yeah.
That shows you where you are right now.
Oh, okay. Yeah, that makes sense.
Okay.
Okay.
So you go to the untitled, and now you can
Yeah,
check
that
your
looks
waveforms, and that looks right.
So you're basically changing.
All right. So at the moment, any other questions? If no, we're going to run the implementation. After we run synthesis, I'll click open synthesizer design and check the results, like what I'm synthesizing. Now you might see this fancy IO map. This IO map is basically the same thing on your FPGAs. If you desolder your FPGA, you will see all the pins on the bottom of the FPGA, but I don't suggest you to do so. If you go to this step, we're trying to make some constraints. This constraint is how to bind your I/O into the constraint file. But in order to do that, you have to check the data sheet of BASYS3. For example, here you can see all the LEDs, you can see all the push buttons, and you can see all the switches. And on the page, if you go to the data sheet, there's a table 2. It shows you which circuits are using what kind of voltages here. For example, all the FPGA IOs are using 3.3 volts. And we have another very important information here, which is the pin W5. The pin W5 gives you the clock. So there is an onboard oscillator that gives you a 100 megahertz clock. So as we have all the informations, I'm going to constrain the I/O. By now, you should see the package and I/O ports on the bottom. If you don't, go to layout and I/O mapping. Okay. So does everybody see this right now? See this fancy I/O mapping right now? Okay, seems no problems in this step. I will proceed to bind. Okay. Sorry, what?
Do we have to fill in the LEDs as well? All of
Yes,
them?
you are going to fill all of them
All of them.
manually. All right, as the question asked, we're going to fill all the LEDs and ports manually, starting with AN. AN means the anodes of the 7-segment displays. You see the AN3, AN2, AN1, and AN0 here on the data sheet, and they refers to W4, V4, U4, and U2. So go to your Vivado and look at your data sheet. Zoom in, zoom in. And you are going to fill the package pin here, like AN3. AN3, we can see that's a W4, so we just type in W4. And for AN2, it's a V4, I type in V4. And it says, okay, that means it's bonded, and U4, U2. All right, so that's all the anodes. And now we're going to fill all the LEDs because we're going to use LEDs. So for the LEDs, you go back to your datasheet and you check which LED and how the LEDs are connected to the Atrix 7 pins. Yes. Oh, yeah. Okay, illegal direction. Oh, you're under OneDrive. Make sure the path doesn't have any special symbols or space. So put it somewhere under, like, not OneDrive.
On the PC itself.
On the PC, maybe on the download
Oh, okay.
or documents,
Okay.
but not the OneDrive document.
Okay, thank you.
Yeah, no worries.
Yeah.
All right, like I just said, we go to the data set, we go to the data sheet, and we try to connect all of them manually. Because if you do it manually, you understand how the pins are connected to the FPGAs. So on the left, you have all the LED names. These are the names you write in the top file. And on the right, you have the package pin. So this file, this block, this procedure is binding your design to the actual physical pin. All right, I'll show you how to fill them manually. All right, so that's all the LEDs, but that's not everything. We have also a list of switches as well. It's a little bit tedious, but we have to do it. Okay.
Yeah.
All right, now we are filling out all the vectors, but other than vectors, we have also have the scalar ports. For example, the CA to CG, these are the cathodes of the 7-segment display. So we fill them again. All right, finally check the clock. As we said, the clock is pin W5. We just put a W5 in here. Okay, we have bounded all the pins, but that's not the end because we also have to set the I/O standard. I/O standard means the voltage you want to work on the I/Os. The default is LVCMOS 18. It means 1.8 volt. But all the I/Os, all the cells are running at 3.3 volts. So we have to manually change it to 3.3, which is LVCMOS 33. Okay. So we change them. There's another way of doing it is you select them all, right click, I/O port properties. Okay. It sometimes doesn't work. I just put in everything manually. And once you have done them all, on the keyboard you click Control S, and that will save the I/O ports. Once you try to save it, it says to save to a constraint. But at the moment you don't have a constraint file, so you have to create a new constraint file at the moment. So when you say save the constraints, click create a new file type XTC, file name constraints, or whatever you would like to put in. And you can put it local to the project, or you can store it somewhere else as long as you can find it. Okay. So there you go. If you go to the sources, you will find a constraints. You have a constraint file. You open it. These are the codes to bind your package pin to the ports. But as we mentioned in the early slides, the constraints has two parts. One is I/O bonding, one is clock. So in synthesis, you click the constraint wizard, and there you are going to set up your clock constraints. You also have already defined that the clock is 100 megahertz. You put 100 here, and you skip to finish. That's everything you need. All right, is everybody still following? You can always post me if you have any questions. All right, So we have all the files, all the code, and all the constraints made. Now we can run our implementation. You just click Run Implementation. And wait it to run again from synthesis to implementation. Vivado is kind of slow. If you don't have a supercomputer, don't have a great computer, it's gonna take so long. All right, implementation is complete. You can open the implemented design. In the implemented design window, you will see some reports and you will see some graphs. For example, if you go to the reports, you can see the utilization is some sort of utilization. Double click, and you have some timing. You have some timing information. You have some power information to see if you run this code on your FPGA, how much power is going to be combusted. And there's some warnings, there's some methodology problems. As long as they're not errors, you are fine. So the final step is generate bitstream. I try to just generate the bitstream. Once you have done your implementation, you see the running right bitstream. All right, now you have your bitstream generated. It asks you to view reports or open hardware manager. Now open hardware manager and connect your FPGA to your laptops. Connect your FPGA to your laptop with your micro USB cable and make sure you turn it on. Okay, there's a switch here near the power. You have to push it up to make it on. While it's running there, let's just double check the hardware manager. Once you are in the hardware manager, on the top right window, you will see this hardware manager label here. Click open target. This is the way you connect your FPGA to your laptop and select auto connect. All right, now you should see your FPGA in the hardware window. Like here, some Xilinx, Vigilant, and you see the FPGA, the chip here. Click program device. And you automatically see the bit file. This is the bit stream that you generated. And click program. Then you will see it is on your FPGA right now. For example, I can make some example tests here with the FPGA. I have some scripts here. The right 4 switches refers to data A, and the next 4 switches refers to data B. And the 9th switches here refers to a C in. Now let's try the first example, 1 + 1 = 2. Sounds hard to calculate, but let's try. So for A, I give it 1, and you can see the result here is 1. By the way, on the display, the left two shows the result, and the third segment shows data B, and the last segment shows data A. So you can see like 1 plus 0 equals to 1. So I give it another 1 at B. All right, now you can see 1 plus 1 equals to 2 here. So that means our 4-bit adder is, everything is running fine. Now let's try next example. Next example is 5 plus 5. Remember what is 5 plus 5? 5 in bits is implemented in this way. So we can see 5 here. I put A0 and A2 to be 1 and A3, A1 to be 0. That gives you a 5. And again, I give it another 5 on data B. You will see 5 here. And the result is A. So that means you have a 5 plus 5 equals to 10 here. You have an A here. Now let's give it the C in. And that means plus another 1. The result is B. And B in hexadecimal equals to 11 in decimal. Now let's try another example. 1 plus 15. So 1 is just a 1. 15, it means 1, 1, 1, 1 in binary. So I give all the ones, which is F. And you can see it's 1, 0 in hexadecimal. That means 16. And now let's push everything to the top. That gives you 15 plus 15 equals to 30. And in hexadecimal, it's 1E. So it is just as exactly what we designed. So finally, let's give it another, give the calculator another C in. That means plus another 1. And you see 1FFF here. So you are reaching the maximum of the calculator range. Now we have tested everything. That means that proves that our 4-bit adder is running in the right way. Now I pause here for a quick minute. If you have any questions, you can stop me here and let me know if you struggle somewhere.
It doesn't look the same for everyone.
Oh, because I asked them if they don't say it, they should automatically say it, but if you don't, in the synthesis design, go to layout and click IO planning. For example, if I click, I close the, I close them, go to layout, IO planning, and or floor planning. It should be IO planning. Okay, somehow it's not showing here as well.
Show up on the screen.
Oh, sorry, what?
Because I know sometimes when you plug it into the that's it. So, yeah.
Yes, it does. But yeah, don't worry. If you leave it somewhere here, it doesn't show on the screen. I think it's fine. Oh, okay.
Use my, I have this one. Let me see.
Yeah, let's see.
Oh, yeah, they should go to the tools and IO planning, auto placing IO ports, which should be IO planning. How come? I guess weird if I close them. Keep, okay, just keep them all there. And okay, that's a good question.
Design isn't wrong.
Yeah, the design is not wrong as long as the IO ports here is they type in everything correct. When if I close IO ports, I go to the layout, IO planning, and
Right, so
oh, okay, yeah, floor planning. Then you should again see all the IO ports. And it must be in the synthesis design window to make all to open the IO.
The question, what is the C in?
Everyone? Yeah, what is the question? Talk to the mic.
I had a question. What is it even on?
It's on, it's on.
Yes, I had a question. What does C in what is it used for in the
Oh,
adder?
in adder, CE means a carry in, because when you try to calculate a full adder, for example, half adder, you can only calculate 1 + 1 = 2.
Uh-huh.
And if you have, but if you have a 2, that means you need 2 bits to represent that, right?
Mm-hmm.
So that gives you another extra bit. So that's a carry bit. So for full adder, you need a C in to take the previous carry.
Okay. Okay, that makes sense. Okay.
Like when you're trying to like calculate 1 + 9 in decimal, you have a 10.
Yeah.
And the new digit, that's a carry.
Yeah, it's a carry. Okay, and then
So that's the carry. And carry ripple means for every single 1 bit adder, you just ripple the carry into the next full adder. So that's how full adder is designed.
okay.
Yeah, no worries. All right. You have finished the design. So we'll get back to the part 3, coursework introduction. Okay, so this is the part we're going to evaluate your performance, okay? Yep. Oh, it doesn't matter as long as you see the I/O ports. Okay, go to layout, go to I/O planning. Okay, then you see the map and I/O ports.
Where can I find the link? Would be on like the lecture capture.
Yes. Because I'm using Teams, I may upload to Keys or YouTube, but I'll send it on Teams once we upload. Okay. Yeah. So
Where do I find it? Like in Outlook or Teams?
Keys.
Keys.
I upload everything on Keys, and if you have any question afterwards, you can ask on Keys as well. Okay, so this is the most important part of this lab. So I'm feel sorry for the ones who left earlier, because this is going to the part that we evaluate you. All right, so I give you a quick introduction about our coursework. So the coursework is about making your own CPU. In this course, you need some prerequisite like logic circuit design, basic FPGA and circuit design knowledge, which I just gave you. And you need the x86 Windows or Linux laptop with Vivado 2025.2 installed. And the suggest skill is project management and Git fork version control. So lab goals, you are going to design and deploy a simple RISC CPU on BASYS3 FPGA. And the deliverables are 1, working CPU. Second, a verification, approval verification. And third, a documentation, which is a report. So you're going to send us your code, your report, and we'll give you an oral exam to make sure you design this. So learning outcomes, A, architecture and microarchitecture, which is exactly the same thing you learned on the course. And B, RTL design and FPGA implementation. So you are going to use your RTL skills and design your own CPU on the FPGA. And the third part is about verification and validation. You are going to write Testbench and test your code, both in simulation and on the boards. And the last part is about professional practice. You have to write your document. You have to write your report about how you design your own CPU. You will have millions ways of designing the CPU. So I don't expect we see 2 exactly the same design. By the way, we're going to use a code checker to check your code. So if one copies code from the other one, we will find it out and we report to the department. Okay, is it a deal? We use code checker. All right, so this is the submission requirements. I put a detailed one on the tickets. I think you already have a student instruction. So this is basically everything we require from you. 1, the project, it takes 40 marks. B, the report submission. You shouldn't write a very long report, and it takes another 40 marks. Just briefly explain how you design your CPU. And the last is the Viva session. You will need to demonstrate and explain your work. You should also answer some questions we prepared related to the coursework and lectures. So that's going to be more like an oral exam. Good. Not working again. Okay. The policies. Just quick policies on our for this coursework. For questions and discussions, post them on Keys forum. Okay. Email questions and other personal communication methods are not accepted. You don't need to worry about asking questions publicly if you are confused. Some others might be the same. And if you see something in the lab doesn't look right, report to the instruction team, see it, and sort it. Lab equipment and management. Students can borrow a BASYS3 development board from the compute support team. Each student will have a BASYS3 board. And for those one who don't have a laptop, you can sorry, the laptop for borrows are only on the labs. But again, we provide another lab at King's building, King's Student Computer Lab. It's opening all the time. You can go there and finish your homework anytime. Students who borrowed this BASYS3, basically everyone has their own FPGA board. You must return them in the right session. Otherwise, we will cap your degree. We'll cap your grade to 80%. Return the boards and laptops before the mark is released. Otherwise, you get 0 for the coursework. All right, group working policy. No group working. Wait, what? Yes. Yeah, it was. Oh, I just let you know. Okay, sure. Yeah, no worry about it. Late submission policy. You should not submit your work late, but the time is to be continued. But I'll make sure I give you enough time to submit your project. Late submission will cap your grade to 60%. No submission after mark release will be accepted. If you have medical excuse, the deadline will be postponed based on the medical proof. So using AI policies, you are allowed to use AI any way you want. You are responsible to your own coursework, not AI. So make sure you understand the code you provided. And you'll be asked to explain your course. You'll be asked to explain your work during the Viva presentation. And we suggest you use Microsoft Copilot, Google Gemini, or ChatGPT, like whatever way, to help you understand the process. And academic misconduct policies. We see misconduct sometimes, but this time we're going to put it hard. Students are not allowed to copy code from others. So that's a simple rule. If project is use any open source code, please indicate them in a README text file. We will use the code checker for all submitted files. So make sure you don't copy codes from any others, or you both could be punished, okay? Make sure your own code is proprietary. If we discover a student who has no idea about the coursework in the Viva session, it indicates the work could be done by someone else. And if we have a clear evidence of a plagiarism activities, we report to the department. Easy? Any complaints about that? Okay, hints. If you want to practice your Verilog, you can go to H2Bits. It's written by another TA from University of Toronto. It's super easy to use and super easy to practice. For Mac users, this is important. You can use Icaros Verilog, which is open source Verilog compiler and simulator. And you can use Open FPGA Loader. This is open source tool to write a generative bitstream to FPGA on your Mac OS. And I suggest you use Git and GitHub to manage your code for version control and synchronization. So coursework introduction, why RISC-ing CPU? RISC-ing CPU is 16 RISC CPU implementation, and RISC stands for Reduced Instruction Set Compiler. And the memory address will be only related to load store architectures. And why RISC-ing? Why not ARMS or MIPS or the LC3 instruction that you learned in the lectures? Is because a standard lecture teach you the analyze the standards, but our RISC-ing lab teach you how to engineering solutions. This is going to be a full stack ownership. You build the entire vertical scale from assembler, data path, control, connecting the codes to the silicon. And it's authentic problem solving. A custom unique ISA means you have no solutions or manual online. You must think like the great CPU architects in the history. and you will face the same problem as they faced in the past. Okay? And if you succeed and you survived from this coursework, you will succeed in the jobs as well. For example, you in the past lectures, if you say I know about ARM programming, others might be the same. But if you tell the company that I created my own CPU and made it work, then you are something special, okay? So that's why I want to push you hard. If you go to Stanford, you go to Berkeley, they will do the same thing. So I wish you just be as competitive as those graduates, okay? So computer architecture, the overview, which is just the same thing we covered in the lecture. Computer is just a factory of data. And the von Neumann architecture is just processor, I/O, memory, control, and data paths. And instructions are used to tell the computer what to do. So instructions from hardware to software. This is a bit tedious, but it's basically everything we covered in the lecture. We have the instructions, rows of instructions, the execution flow, including fetch, decode, execute. We have different types of instructions, and we are going to implement them one by one. And a quick recap on the endians. Our design will be a little endian architecture. So make sure you understand what endian means. We have already talked about this in the first tutorial, so I'm not going to rephrase it here again. So this is the risking CPU instruction overview. This is all the instructions that I will post it later on Kids. It was an Excel file, and you can download it and read it. So this is all the encodes of the risking CPU instructions. Make sure you understand what's in the lecture, and make sure you migrate your knowledge to this table. Because as a CPU architect, you are not trying to memorize one architecture. You are the architect that understands everything about CPU, so you can design your own CPU or analyze your CPU in a future. So this will be our first task. It's going to be ALU design. As we mentioned in the lecture, ALU is the center of processing. And this is the structure for the top file. I will provide a template project, so you don't have to worry about what we did in this lab. But this lab is help you to understand how Vivado workflow works. So if you see something doesn't working, you can debug yourself. The blocks in the red, these are the blocks you are going to implement. So basically, we have shifter and we have an ALU. All right, so this is the ALU design and opcodes. For this ALU, it's going to be a 16-bit ALU, take 2 operands. And we have a 3-bit operand telling the ALU what to do. And these are the 8 movements that the ALU can do. But by the way, we also accept one C in. This is a carry bit in. So this processor can expand to some more complex data structure, like 32-bit data structure. And this is something we didn't cover in the lecture. These are CVZN flags. These are the flags telling the status of the result. I will explain it later. So N means negative. N gives a 1 if the result is negative, and 0 if not. And 0 means if the output is 0, and the flag is 0 if it's not. And carry bit will be 1 if there's a carry out, and 0 if not. And this is the hard part. It's about overflow. 1 means there is a overflow, and 0 means if not. So recap on overflow. Overflow means we have a 16-bit of data, but we calculate something that overflows to the other ranges. For example, 8-bit number value is between -108 to +127. If you try to calculate 70 plus 80, the result becomes negative. And this is where the overflow happens. So for unsigned addition, the carry means just means overflow. But for signed addition and subtraction, a V bit means a overflow. So the question is, how do we design the V flag? There are two ways to think about it. The hard way is analyze all the status and find out the way to do it, which I already give you the circuit design, which is just take the XOR of the last two carry bits. If you want to know more, you can read the page on the right. But to help you understand it, if you think about adding both inputs that are positive, but the result become negative, this means overflow happens, or both inputs are negative, but the result is positive. That's an overflow. Or you try to subtracting. If A is positive, B is negative, you should get a positive number. But if the result is negative, that's an overflow. Or if A is negative, B is positive, you try to A minus B, but you get a positive result, that means overflow happens. If you want to know more about the details in ALU design, you can refer to a book called Digital Design, a System Approach. All right. The next thing we are going to design is a shifter. The shifter is a simple shifter that just shifts the codes. For example, if I give a 0, 0, it means just pass through. The output is just the number that goes in. But if the opcode is 0, 1, it means logical shift left. So this step basically means multiply by 2. And if you have logic shift right, it just shift everything to the right and fill a 0 on the MSB. In unsigned numbers, it means divide by 2. And we also have an arithmetic right, which is we shift right, but we copy the MSB to fill the new position. So that gives you a arithmetic divide by 2. So this is what you are going to design, a shifter and an ALU. And you can use the provided demo project and fill your own code. You will need to write your own test bench to prove it works. You should download the project to FPGA and show it works. So a quick demo here about the ALU you are going to design is here. Oh, sure. Okay, for the ones who borrow laptop, you can return the laptop by now. I will show you the demo at the same time. At the moment, you will not need the laptop. You can return them by now. I will just program the device to show you how it works. All right, I believe it's there. And based on top level design, this is how it looks like. I will show you how it works. So when you try to play with yourself, this is going to be something like this is test 1. So this is the ALU. It's already implemented, but I won't give you the code. You have to implement them by yourself. So on the top, I'll try to give a number to register A. For example, 5. I give a 5 to store to register A. You can see a 5 here. And for register B, I take another 5, which is 5, and store them to register B. And you see A at the output, because that's, for now, this display shows the output. And for the operands, for example, next time I try to do a multiply, like 5 plus 5 times 2, I gives the shift to the operand, and you see the result is what 15, which is F. Okay, because we don't have too much time here, I'll upload this sheet online so you can play with it yourself. You can play with all the examples to make sure your ALU is working in the way that you want. So this is everything from our lab 1. And from after lab 1, I expect you to finish the ALU design in 1 week before lab 2. Because lab 2, we're going to use the ALU that you designed to implement the CPU data path. So make sure you have everything prepared. Although I'm not going to examine you on the next week, I hope you make it ready, okay? Now, if you have any questions, you can ask me. If you have borrowed a laptop, please return to the technician right now. Yes. No, full array is just for practice. You are going to finish ALU and the shifter. And I have already provided you the demo project. You can download the project and then fill the code.
For the code, can we use like GPT or anything?
Yes, as long as you understand what you are writing.
Okay. So basically, I understand all the opcode and everything in the laptop.
No, also the codes you are writing. We're going to ask you to explain your code.
Even during the presentation, right?
Yeah, last session we're going to randomly ask you to explain your some codes. So make sure you understand how to write Verilog. I mean, you can use AI to help you, but make sure you don't let AI to overwhelm you. Okay.
Base, like how ALU shift is.
It's not storing. It's like downloading to the FPGA and make it running on it. But the programs are written in Verilog, and you use Vivado to program them on the board. So we can play. Yes.
Then,
If you're trying to do some simulation, you don't need the FPGA board. But if you want to try to play in the hardware, you need to understand the top file and program to the BASYS system.
end of the day, our CPU is going to build on this.
Yes.
So this is going to contain our CPU.
Yes. And also your memory as well. You will also build a memory system on it, which contains some sort of program that you write by yourself. So you see the program is running on the FPGA.
CPU, this same as like the computer CPU, or it's like a simple version?
A very simple version. Very simple version.
Because of this, right?
Yeah, it's very limited logics. Okay.
So and when I build the ALU and everything, I just do the slides, right? And just
Yeah, follow the slides, but I'm not going to show you exactly the way of building an ALU. I expect you to do it yourself. Okay. Yeah, no worries. You can ask questions on kids. No, the kids. Yeah, the kids forum. And I'll regularly check if there's any questions posed, and I'll answer it if I have time. All right, return your laptops. Return your laptops. 我们基本重构了这整个 LOD 和 HAD 的那个课程，所以基本上以前的 HAD 现在放在 LOD 里面，然后 HAD 我们会讲这个计算机架构、计算机组成原理相关的内容。
就其实它有一些基础前置课程。
对，所以 LED 其实基本上是 HAD 的前置课程。
对，上学期没有这个。
好像有没有这种？但事实上这样，如果实际上我第一个 lab 就是给就是没有设计基础的人开的。
刚才在下面。
哦，没事，反正我这个录了课之后，我会传到 YouTube 上面或者传到 Kids 里。